Hello, my name is Isaac Klein, and I'm a junior studying electrical engineering at the University of Pennsylvania. In this video, I'll be discussing spin transfer torque random access memory. In order to get started, it's important to talk about spin transfer torque, which is the basis of Stt-Mram. Charge carriers have spin, but in general, electric current is unpolarized due to having both types of polarizations which cancel out. Here in this image can be seen that there is a spin polarized current, which is due to the magnetic tunnel junction, seen here. Magnetic tunnel junction is made up of two ferromagnetic layers and a thin isolating layer allowing for tunneling, which is generally made of magnesium oxide. The ferromagnetic materials are able to retain magnetic polarization when subjected to a strong enough magnetic field. In the magnetic tunnel junction, one of the layers, here on the left, is a permanent magnet with a fixed spin orientation, and the other one is free, meaning its orientation can be realigned. In the middle, a thin isolating barrier allows for tunneling magnetoresistance, which modulates the resistance of the magnetic tunnel junction depending on the state of the two ferromagnetics. In order to change the magnetic polarization of the second free ferroelectric layer, current is passed into the first fixed ferroelectric magnetic layer, which then sets a spin polarized current which is aligned to its magnetic polarization. That spin polarized current then flows into the second ferroelectric and is able to exert a torque on the second ferroelectric spin. This can reorient the polarization of the second ferromagnetic layer. The key takeaway from this is that using spin transfer torque, the second free layer can be realigned without exerting an external magnetic field. In this image, the density of states can be seen as the spin polarized current flows through the fixed layer and free layer. In this image here, the case of the magnetic tunnel junction being in the parallel state and anti-parallel state can be seen. In the parallel state, the magnetoresistance is low and a digital logic 1 is stored. In the anti-parallel state, the magnetoresistance is high and a digital logic 0 is stored. In order to set the magnetic tunnel junction to the parallel state, electrons flow through the fixed layer first, setting their spin orientation to the orientation of the fixed layer, and then they flow to the free layer, setting the orientation of the free layer's polarization to be aligned with the fixed layer. In order to set the magnetic tunnel junction to the anti-parallel state, electrons flow through the free layer first, resetting the orientation of the free layer to be unaligned with the fixed layer. Reading can then be done by selecting the cell's word line to turn on the transistor seen here in the right-hand image, and applying a voltage between a bit line and source line, causing an amount of current to flow which depends on the state of the magnetic tunnel junction. This current does not change the polarization of the free layer as it is not strong enough. Writing is also done by selecting the word and bit line, but with a greater magnitude of current, which will depend on the material of the tunneling barrier. In order to understand the potential benefits of Stt-Mram, we should first talk about magnetoresistive random access memory. Magnetoresistive random access memory operates in the same way as Stt-Mram, but with the application of an external magnetic field to set the free layer's polarization, as can be seen in this image. MRAM is seen as a possible universal memory in the future due to its speed, reliability, and low power consumption. Stt-Mram improves on MRAM with its compact architecture, which does not require large currents to create magnetic fields, and it is less susceptible to disruptions because it doesn't require the external magnetic field that MRAM requires. Stt-Mram also, its architecture, has better scalability, which makes it a great option going forward with MRAM. Here, a comparison of Stt-Mram and Toggle MRAM done by Avalanche Technologies can be seen. In performance and endurance, the two technologies are similar, but in data retention, read current, write current, and density, Stt-Mram Stt-Mram is far better. Now to talk about the history of Stt-Mram. In 1996, John Sasuke and Luke Berger both independently predicted the phenomena of STT and began to develop the theory. In 1997, Sony applied for a patent for Spinor, which is spin-polarized, injection non-volatile, orthogonal, read-write random access memory. Spinor was a forerunner of Stt-Mram with different design but similar principles. In 2006, Everspin released their first commercial MRAM chips, and in 2009, Hitachi and Tohoku University demonstrated 32 megabit Stt-Mram. In 2011, Qualcomm showed a 1 megabit embedded Stt-Mram, and in 2016, Everspin sent samples of their first 256 megabit Stt-Mram to customers. In 2019, Everspin began their production of 28 nanometer 1 gigabit Stt-Mram chips. And currently, IBM, Samsung, Everspin, Avalanche Technologies, and other companies are developing Stt-Mram chips. To continue discussing the motivations of Stt-Mram, we can make comparisons to competing technologies, particularly DRAM and SRAM, which are volatile forms of memory which require a continuous supply of power to store data, and like standard forms of memory, DRAM and SRAM use electrical charge. As discussed earlier, Stt-Mram is non-volatile and uses magnetic polarization to store data. Stt-Mram has many of the benefits of other competing technologies, such as near-zero leakage energy and similar non-volatility to flash memory, meaning it essentially lasts forever. Stt-Mram also has fast reading and writing times, which are comparable to the reading and writing times of DRAM. Stt-Mram can also be seen to have endurance comparable to SRAM and DRAM, making it a reliable option for long-term applications. In terms of the development of Stt-Mram, the future is very bright, but some challenges must be addressed before Stt-Mram can be heavily relied on. The first issue is reducing the write current, which is less than that of MRAM, but still should be reduced to further decrease power consumption. In the graph on the right, the future projections of the current as devices are scaled down can be seen. The graph shows some uncertainty, but ideally the currents can continue to decrease as devices are scaled down. Another issue is scaling down, which can cause read disturbance switching. This is when, as devices are scaled down, read and write currents shrink and are closer together, and this causes reading to affect neighboring cells and potentially change their states. Although reading current is much smaller than writing current, a prolonged reading current can still cause an effect in the polarization of the other cells. Another issue is barrier breakdown. The thin magnesium oxide layer can break down due to voltage stress, and as seen in the graphs below, the step size of the voltage can affect that. Another issue is the variability of the smaller size cells, which can be inconsistent. Continuing the discussion of the future of Stt-Mram, spin orbit torque MRAM is a similar technology which could challenge Stt-Mram. SOT-MRAM works in the same way as Stt-Mram, but uses an in-plane current in an adjacent layer to write to the device, and the reading process is the same. SOT-MRAM is a newer device, and so research is still being done by companies like TSMC and others, and SOT-MRAM is said to have the potential to be faster, denser, and more efficient than Stt-Mram. To finish off, I'd like to talk about some of the applications spin transfer torque random access memory has been applied to and is being applied to. Some examples are electric vehicles, artificial intelligence, satellites, and wearables. This is all because of the high speed, reliability, and endurance of Stt-Mram. I hope you enjoyed my presentation and you learned about Stt-Mram. Thank you.